All right, cool. Thank you all so much for coming. I know I stand between you and Bridget, so I'll go as quickly as possible. Today's talk is like fun and lighthearted. I'm going to make fun of Kubernetes a lot, so just bear with me. Please laugh at my jokes, even if you don't think they're funny. It's for my own personal self-esteem. Cool. How many people have heard of the Kubernetes? How many people are running it in production? OK, that was a lot less hands. How many people are running their own Kubernetes in production, meaning not like a cloud provider or a managed version? Cool. So this talk is really for all of you. So the rest of you can just hang out. But I promise I'll make it fun and entertaining. This talk is about how encoding and encryption are not the same thing, but there's some background that I have to go through first. My name is Seth. I work at Google. I've been at Google about 2 years. Prior to that, I worked at HashiCorp. I was there for 4.5 years, so Rosemary's talk resonated really well with me. That's my Twitter handle, my Google email, my LinkedIn, my Facebook, my phone numbers. That's not my phone number. But feel free to tweet at me. My DMs are open. If you have questions that you don't feel comfortable asking here on the microphone later or on the public internet, you can always DM me or email me at google.com. Cool. So let's start with the question in the room. What is a secret? And I did this talk a while ago, and I found that I have to set this level base ground because people come in with these assumptions of what I'm talking about when I say a secret. So for the purposes of this talk, a secret is a credential, a configuration, an API key, or some type of information that an application or service needs at build time or runtime. So think like a Twilio API key in order to talk to to send a text message, or a Mailgun API key in order to send some email, for example, or a service account to talk to a cloud provider. Specifically, we're not really talking about like credit cards or social security numbers, although they could apply here. We're really talking about like application level secrets. So given that, why do we protect secrets? To put it another way, why is Twitter not our secrets management solution? So, right? There's an API, they're versioned, they're immutable, you can't edit them. So there's, why not just publicly store our secrets? Well, there's three main reasons. The first is that secrets are an incredibly attractive target for hackers. But why? Well, the reason is that they are often leaked or accidentally included in repositories or storage buckets. If we look at a lot of like the recent security incidents, they've been a result of like an S3 bucket that wasn't properly secured, that included a credential that could then be used to elevate access to GitHub to gain access to source control or customer data. And I'm not like talking down on S3 or GitHub, right? This is a security issue, but these are the ones that we're seeing more frequently. The reason this tends to happen, though, is that secrets often include overly broad permissions. How many people here work at or have worked at a thing that was called a startup? Right? When you work at these things called startups, right, you have this thing called VC money, which is like monopoly money, but real. And they tell you, like, make this product, right? And make it fast because I want like a 10x return on my money in the next 3 days. So oftentimes, when you're in a startup, and I've been there, I've been in quite a few of them, there is no like principle of least privilege, right? It's like, oh, new employee, here is root on all systems. Please let us know if you need more. Right? And it's like the old XKCD comic, which is like, make me a sandwich. No, sudo make me a sandwich, right? It's like that, but for everything, the HR system, the spreadsheets, prod. And then like 6 years later, when you're a real company servicing enterprises, you're wondering like, well, how did we get hacked? I don't understand. All of our employees had root access. Shouldn't they have been like, stop this from happening? So this is why we care about protecting secrets. They often include overly broad permissions. They're easily leaked, even with like the best security practices. It's very easy to leak these. For context, like I've worked in the security industry and the DevOps industry for quite some time. About like 2 years ago, I pushed my dot files up into a public repo, and I was like, hey everyone, check out my dot files. Like I have this really cool terminal theme. You all should use it. And I accidentally pushed up my .Heroku folder, which includes my Heroku credentials, and then everyone was able to like access all of the apps that I had access to in Heroku. And that was just like an accident, right? Even people who think about this all the time make mistakes. So given that, we have to protect secrets. And there's 4 key ways in which you protect secrets. The first is encryption. I know that that's not the first on the slide. The first is encryption. We want to encrypt secrets in transit and at rest. The second is rotation. If we assume that at some point a credential is going to be leaked, whether that's on purpose or accidentally, we have to have a process in place for rotation. And this can't be like a yearly process that causes 6 months of downtime to your app. This has to be something that you can do on a regular basis, like weekly or monthly, something that happens in process with 0 or very little downtime. The third thing we have to do to protect secrets is we have to isolate them. We want our secrets to be stored separately from where they're accessed. Basically, we want to make it as hard as possible for an attacker to gain access to the secrets. So the easiest way to do that, or one of the easiest ways to do that, is to store them separately. And then the fourth way in which we protect secrets is by assuming that we're going to be hacked, assuming that someone is going to make a mistake, again, intentionally or unintentionally, and building rich and verbose audit logging into our system. So if we just do all of the three, right, it's like building a giant castle that's super fortified, and then you assume that like you're secure. So that whenever the enemy penetrates your castle, you're like, well, I don't know what to do now. I didn't plan for that. Or you have no visibility into it, right? It happens in the middle of the night. You assume that your castle walls are impenetrable, so that when someone penetrates them, you have no idea what to do. And this is where the fourth part of protecting secrets comes in, which is just assume that your secrets are going to be compromised. So make sure that you have visibility into when that happens, and make sure you have a plan to recover. This talk is going to focus on encryption specifically with respect to Kubernetes. Now, it's important to note that the other three are not less important. They are all equally important, but I only have like 30 minutes, so we're going to talk about encryption. Also, the other three don't lend themselves to quite as many jokes, so we're gonna stick with encryption. Just like there's multiple ways to protect secrets, there's multiple ways to do encryption. So some of you are probably familiar with like machine-level encryption or file system encryption. This is like Apple's File Vault, or like the Secure Enclave on your iPhone or iOS device. And then like as we move further up the stack, right, or I think it's BitLocker on Windows, there's like one key or a key ring that encrypts the entire device, right? And if an attacker is able to like brute force that key, they effectively decrypt all of the data on the device. If we go higher up the stack, though, we get towards things like service-level encryption and application layer encryption, which is instead of the disk being encrypted with like a string, some high-entropy string, instead we're going to encrypt every file with its own unique key, and we're going to centrally manage those in some external system. And generally, we want multiple layers of encryption, right? We want to encrypt things at the file level, but then also at the operating system level or at the disk level. So usually you want 2 or more layers of encryption. This talk is specifically going to talk about application layer encryption or app layer encryption. So app layer encryption is applied at the earliest possible step. Basically, with app layer encryption, you define a contract that says any secret in my application only ever exists in plain text within the bounds of my application. So if someone gives me a secret, or if I'm storing a secret, that secret is only ever in plain text in my application in memory. And if it ever leaves my application, such as like an outbound API response or some type of external API call, it is encrypted. This provides a very granular protection level because every secret, or every secret for every version of your application, can be encrypted with a different string. So that if an attacker is able to, say, brute force or gain access to that key, they can't decrypt everything else, right? It's like a unique encryption key for every secret that you have. This also protects your data as it moves throughout the system. So we always want to encrypt secrets via TLS in transit. And we want to encrypt them when they're at rest as well. But with application layer encryption, you encrypt the secret before it leaves your application, and then you encrypt it again in transit with like TLS or some type of like SSL type thing. So even if you have a developer who makes a terrible mistake and makes an insecure HTTP call, right? They're not using HTTPS. Your secret is still protected because it's never transmitted in plain text, even if the request itself is in plain text. OK, so that was a lot of stuff. What does any of this have to do with Kubernetes? You all were like, there was Kubernetes in the title, and he's talking about secrets. I don't understand. Well, it turns out that Kubernetes has defaults with respect to how it handles secrets. And as you can see by the 4 masks on the screen, they're not very good. So I'll preface this by saying, like, I'm not trying to scare anyone, but like Kubernetes is insecure by default, particularly with respect to how it handles secrets. In Kubernetes, when you run kubectl create secret or the associated API call, your secrets are created They are Base64 encoded, and then they are stored in plain text in etcd. If you're not super familiar with the internals of Kubernetes, that's fine. etcd is kind of like the file system where Kubernetes stores all of its data. It's not actually a file system, but you can think of it that way. So this is basically like me telling you a secret, you writing that secret on a Post-it note and putting it in your pocket. And then anytime someone comes to you directly and says, what's the secret? You're like, no, you don't have authorization. I need to see your RBAC policy. But someone could just get the note out of your pocket directly and never even talk to you. And this is, anyone who has access to etcd has access to all of your secrets in plain text. It doesn't matter your RBAC permissions. It doesn't matter your network policy. It doesn't matter your pod security policies. Like, none of that matters. Because at the end of the day, once you have access to etcd, you have access to all of this data in plain text. Now, I will also say that if you're running a cloud provider managed Kubernetes, this behavior might be changed. And we'll talk about ways in which you can change this yourself and some of the defaults that exist in some cloud providers. But if you're running like a straight up Kubernetes cluster today, like you run kubadmin, you spin up a cluster and create a secret, that secret's in plain text. It's Base64 encoded, but not encrypted. And we'll talk about that in a second. So I have really pretty animations because security is hard. We're going to look at like this architecture diagram a few times. So the credit card is the secret. I know I told you that we weren't talking about credit cards, but that was like the best picture that I could find. We have the Kubernetes API server, which is like making the API call, and then etcd, and then those are surrounded by the master node or the VM that's running the Docker containers here. So when you run kubectl create secret, you give that secret to the Kubernetes API server. The Kubernetes API server will always see your secret in plain text. That's kind of like the API contract. The Kubernetes API server will then Base64 encode that data and put it into etcd. How many people get my joke? OK, I thought it was funny. There's two equal signs. Come on. And then we're going to see my favorite character in this entire charade, which is the red raccoon. And the red raccoon represents an attacker. And in this example, if an attacker has access to etcd, they have access to all of your secrets in plain text. Doesn't matter what policies or permissions you've set up on Kubernetes, because they've just straight up bypassed that. And if you confuse encryption and encoding, because Base64 is encoding, like UTF-8 or ASCII, and encryption, if you confuse those two things, you get this thing that I like to call encryption. Every time, people, I love it, right? It's the best thing. Encryption is what happens when you confuse encryption and encoding. Now, you're probably thinking to yourself, well, no one would ever do this, right? Hypothetically, there are websites out there that are kind of like NetScan for the internet. Shodan is one of them. And you can go on Shodan and find publicly exposed etcd servers. Now, it's worth noting that like etcd has uses outside of Kubernetes. But you would be surprised the 286,000 publicly exposed etcd servers out there that have Kubernetes secrets in plain text. Someone told me that. I definitely did not look that up myself right before this talk. My point is that some of this stuff is really hard. But worse, it's really easy to mess up. It's really, really easy to make a very simple mistake and accidentally expose all your secrets to the world with this default configuration. So let me show you this. Who's excited? Just you two. That's cool. All right, so we got a mirror, our built-in thing here. All right, so what I have here is I have Kubernetes running in a virtual machine. It's straight up Kubernetes. There's no multi-node, but I spun it up with kubadmin, didn't configure anything else. These are like the base configuration, base defaults. So I'm going to pull out my cheat sheet. Cool. So kubectl get pod. There's a slight delay, and it's really messing with me. All right, so there's no resources. There's nothing running in this particular Kubernetes cluster yet, but let me go ahead and create a secret. So I'm going to run create secret, generic. We'll name this demo from literal. Let's see, username equals. What should our username be? What? DevOps, OK. From literal equal. What should our password be? 001122334445. Is that right? Yeah. Cool, so we've created this secret, right? How many people feel more secure? I'm always insecure, it's fine. And then what I'm going to do here is I'm going to use a command line tool called etcd cuddle. Similar to kubectl, it's pronounced cuddle. If you say it any other way, you're incorrect. And what this is doing is it's making an API call under the hood. So when I run etcd_cuddle, you could actually replace this with curl -- many other flags to specify CA certificates and a bunch of stuff, and then localhost, because I'm just querying the local etcd server. And I give it a path, which is registry, secrets, default, which is the namespace that we're in, and I named this demo. So this is running, and we get back this thing. Now, you'll notice that there are some, what I like to call Super Mario Kart item boxes, which represents security for this talk. Anytime you see Super Mario Kart item boxes, that's secure. More is better. But you'll notice in here that our password is like just straight up in plain text right there. And this is, if I like pipe this text dump, you'll see there's like some binary characters in here. But the password is in plain text, and the username is also in plain text right there. So even if I shut down Kubernetes right now, all of this data is in plain text in etcd. Worse, it's also in etcd's write-ahead log, which is how it maintains consensus. And if I back up this file system, for example, if I make a backup of the volume that this is on, it will also be included in that backup of that file system volume. Cool, so hopefully everyone is super paranoid now. Now we need to talk about this thing called envelope encryption. So I'm going to do one of those things where I'm going to like talk about something for a little bit, and you're going to be like, I still don't understand how this has to do with Kubernetes. I promise it comes back. Also, there's some really dope animations, so just be ready for that. So envelope encryption is this really cool thing that involves 3 pieces of information. The data, which will represent via a blue credit card. The data encryption key, which will represent via a red key. And the key encryption key, which will represent via a green key. I tried to pick colorblind-friendly colors. So blue, red, and green. That was the first animation. Feel free to like ooh and ah as these happen. With envelope encryption, you basically take your piece of data, you generate a key encryption key, and you encrypt the data. Then you have some centrally managed key, which is your data encryption key, and you encrypt your key encryption key with that. And then you put those 2 pieces of data together, and you put them in like the file system or etcd or whatever, and you store them together. And then when you want to reverse that process, you split them apart. You use your data encryption key to decrypt the key part and get back your plaintext key encryption key. And then you decrypt your key encryption key to get back your plaintext data. And then you rotate your data encryption keys frequently, and you generate a new key encryption key every time you write new data. So envelope encryption, to kind of like summarize in text form, you generate a new data encryption key for each new data entry. You can crypto shred, because you can revoke your key encryption key at any time, and then all of your data encryption keys are effectively, you can revoke the key encryption key or the data encryption key, and they're both gone at any time. And you can easily version and rotate, right? Because your key encryption key is managed separately from your data encryption key. OK, so what does any of that have to do with Kubernetes? Well, in Kubernetes 1.7, we actually introduced the concept of envelope encryption into Kubernetes core. It's not the default, but you can configure Kubernetes like this. Y'all thought you weren't going to see YAML. There was Kubernetes in the title. Come on. So this is an encryption configuration, or an encryption provider configuration, that defines how Kubernetes should encrypt resources. It's also worth noting that I'm only encrypting secrets, but you can encrypt other things, like config maps if you wanted to. But I'm choosing to encrypt secrets, and then I put my encryption keys in here. So my key 1, key 2, those are the encryption keys that I want to use. And then the parent field there, like AES, CBC, and secret box, those are the algorithms that I want to use for encryption. Then when I start up my Kubernetes API server, I pass in this encryption provider config flag to that YAML file. And moving forward, Kubernetes will do this. So now there's a new actor in our model. We're going to put our data into the Kubernetes API server. The Kubernetes API server is going to delegate to that encryption provider configuration file. That encryption configuration is then going to encrypt the data and store it in etcd encrypted. Sounds pretty great. So if an attacker, again, the red raccoon, is on our etcd node, say we have a publicly exposed etcd server, or they somehow gain access to our etcd data file, none of that data is available to them. It's all encrypted. But what if the red raccoon has access to the master VM, or like a backup of the file system of the master VM? There's a few disadvantages here. So first, you have to generate those keys yourself. And that YAML file, you have to run like the crazy OpenSSL command to generate a 32-bit random entropy key. You have to Base64 encode it. Key management is your responsibility. Anytime you edit that file, the Kubernetes API server has to be restarted, which could cause a little bit of downtime. If you mess it up, it won't come back online, and then you have an operations outage. So rotation is a little bit tedious. There's no HSM integration, so if you work in a highly regulated industry like healthcare or finance or government where you have hardware security modules, you can't connect YAML to an HSM. I've tried, it doesn't work. But there's like a really big drawback here, which is that the underlying encryption key is still stored in the same system that the data is stored in. If we went back to like the earlier slide where we talked about isolation, this is why isolation is so important. Because all you've done here is you've given an attacker a really, really good laugh. They're like, ha, they tried so hard to encrypt it and then gave me the keys. This is the equivalent of like locking your front door but then leaving the lock in the door. Right? Or like, oh, it's locked. I could never possibly get inside even though the key is literally sitting inside the door. So there's a huge drawback here, which is that from a security modeling or a threat modeling perspective, you haven't actually improved your security posture. You might have checked a box, right? You might have checked some security and compliance box for your privacy organization, but you haven't improved your actual security posture. So Kubernetes 1.10 came along and introduced this concept called a KMS encryption provider. Still part of that provider configuration introduced in 1.7, but this allows us to delegate to external plugins. And these plugins can do anything as long as they satisfy an API contract. So notice that there's no encryption key in here anywhere. Instead, I'm delegating to like a Unix socket or an API. So what does this look like? Well, we take our secret data, we give it to the Kubernetes API server. The Kubernetes API server then goes to the encryption configuration. The encryption configuration, though, doesn't really know anything. It's kind of like a dumb proxy. It goes to the KMS service. And this could be like a cloud-provided KMS or something like HashiCorp Vault or CyberArk, some type of key management service that you're operating. You get back the ciphertext, which gets stored in etcd. And when you reverse the process, it's the exact opposite. The Kubernetes API server requests the ciphertext. The encryption config goes out to the KMS service to decrypt it, get the plaintext back, and the plaintext goes back to the user. So if a red raccoon happens to gain access to our master VM, we have protected against like 3 of the 4 possible mitigations. So a publicly exposed etcd server is protected because the data is exposed, or the data is encrypted inside the etcd server. A backup of the file system is protected because the keys are not stored in the file system. And a backup of the etcd data file is also not accessible because the data is encrypted. But what if an attacker gets access to a live virtual machine that is currently running? We haven't mitigated that, and that's actually really hard to mitigate. We can protect against offline attacks, but our master VMs need the ability to talk to the key management server. So this is where we jump into like the auditing side of things, which is if all of a sudden we start seeing like 10,000 requests to decrypt all of our secrets, we should probably throw some type of alert and say like, hey, there's probably someone who has unauthorized access to do this. We can also introduce like rate limiting and quotas and potentially even use like AI or ML to detect what normal use looks like and flag any abnormal use. But we can very easily mitigate 3 of the 4 attack vectors. And then we can also mitigate access by creating like private Kubernetes clusters that don't have publicly exposed IP addresses, make sure like we're not allowing anyone in the company to just SSH in randomly. So you might be thinking to yourself, this sounds hard. How am I going to do this? I don't want to build a plugin. You can write plugins in any language. It's easiest in Go because you can share the same structures. But you can write them in any language. Every major cloud provider either has one that they have built or a community version of that. So Google, Azure, AWS, and then Oracle has one that works with HashiCorp Vault. Like mandatory vendor pitch for a minute. If you do this on GKE, there's like 3 flags, and we do all of it for you. You don't have to install anything. There's one final thing I want to talk about, which is like the initial secret problem. How do you authenticate your master VM to talk to KMS? Well, this is where you trust like identity and access management on your cloud provider. So you delegate privilege and access management to your cloud provider's IAM system. That gives you like that initial root of trust. And then from there, you can separate concerns, right? etcd nodes don't need permission to talk to KMS. So I'm going to show you like a really quick demo, but I'm running short on time. We started like 2 minutes late. So I'm going to have 2 more minutes. They're not saying no, so we're just. OK. Cool, over here. So what I'm going to do is I'm going to edit this manifest file, Kubernetes manifest, and it's the Kube API server. Cool. Gotta go to startup mode. All right. And then I have to face ID because security. Cool. So in here I have the encryption provider configurations for both KMS and local. We already talked about local being terrible, so we're not going to do that one. I'm just going to uncomment this, and I'm going to save this file. Kubernetes is really nice in that if you make a mistake in this file, it automatically restarts the Kubernetes API server for you. So that like if you make a typo, you incur downtime. It's really great. But I don't have to restart the Kube API server. In the meantime, we will look at the actual config, which I don't remember where I put it. It's in PKI. Encryption, KMS. So this is almost identical to what you saw on the slide. It's a different Unix socket path, but other than that, it's identical. And hopefully this is restarted now. If we do kubectl get po dash all namespaces. Cool, everything's happy. So if we run kubectl delete secret, what do we call it, login or demo or something? Demo? Demo, okay. Deleting the old secret, that way we get rid of that plaintext. And then I'm just gonna hit the up arrow a couple times just to prove to you that it is completely the same command. I'm gonna run the same command. Notice as an operator or like a developer interacting with Kubernetes, my experience remains unchanged. Same exact command as proof by bash history. I'm gonna run etcd get, again, same command. So many Super Mario Kart item boxes. There's at least 1 star in there. But in reality, there is some plaintext data in here. For example, like the name of the plugin and the version of the key that we used. We consider that to be metadata, not actually the secret data. But the actual like login username and password are obviously encrypted, as indicated by the Super Mario Kart item boxes. Also, there's just like an N here that's like outlined. That's pretty cool. Anyway, so let me jump back to the slides really quick, and then I promise I'll end. So you can also do this with Vault. Or like any on-premise secrets management solution. It's identical, except you replace KMS with Vault's transit backend, which I was also going to demo. I have time. They're not going to kick me off the stage. So I have this lovely script that creates a secret in Vault. It's a little bit bigger. Oh, I created a secret. And then I have this script that accesses the secret in Vault. And you can see that it's basically the same. It's obviously a different payload. But in here, you'll notice like there's a little bit more metadata. Vault needs a little bit more metadata to know what key and what version of the key, as well as where the transit backend is mounted. But it's identical, so you can run this on-prem, or you can use a cloud provider managed KMS. So in summary, so you like that? It's a sad face that moves to a happy face. So in summary, you should use at least 2 layers of encryption. Always rotate your keys and rotate your secrets regularly. Use envelope encryption. It's an incredibly scalable way to actually do encryption. And you should definitely protect Kubernetes secrets using an external key management service provider, or check with your cloud provider and see if they have options to enable this by default. Thanks. That's my Twitter handle. I don't think I have time for questions, but I'll be around the rest of the day. Thanks.
Thank you.